Hi everyone, my name is Rina Leibovitz and I'm going to present the work Dynamic Length Factorization Machines for CTR prediction. This was achieved collaborating with my colleagues at Yahoo, Yochai Kaplan, Neil Cohen, and Oren Samech. In this presentation, I will demonstrate how we optimize our CTR prediction model by dynamically changing its length, but our approach can be applied to other factorization machines as well, as described in the paper. Our team at Yahoo, the Gemini native science team, is in charge of Yahoo native advertising. What's a native advertising? A native ad is an ad that resembles its surrounding native content. As you can see in the example here, this is a native ad on Yahoo homepage feed. Unlike the search ads marketplace, where we present ads knowing what the user was searching for, native advertising is considered to be more challenging in general, since the user's intent during page visits is unknown. So how do we choose which ads to present to our users? So why am I seeing this ad? Given a user and a pool of possible ads, our mission is to calculate for each ad the predicted click-through rate, the PCTR. In simple words, we need to calculate the probability that the user would click the ad. How do we calculate this? When a user arrives, a vector that represents this user and vectors that represent each one of the ads is being retrieved from the model. These are the latent factor vectors that the model learns during training. The inner product of the vectors would be used to compute the PCTR in the following way. So the PCTR is calculating using the sigmoid function, and you can see the inner product of the user and the ad vectors in the exponent. So the larger the inner product is, the larger the PCTR is, meaning that there is more chance that the user would click the ad. We would come back to this formula later, but now let's dig a little bit deeper into the user vector itself. Since the data we're working with is very sparse, the model doesn't keep and train a vector for each of our users. Instead, it holds vectors for each of the user features. And when a user arrives, we create its user vector based on his feature. So for example, here is a simple model that has only 3 features: gender, age, and hour. When a 20-year-old female is checking her mail at 11 p.m., we would take the appropriate vectors. We would take the female vector from the gender box, we would take the 20 vector from the age box, and we would take the 11 p.m. vector from the hour box. We would combine these vectors to create her user vector. How do we do that? Originally, we had a static uniform mapping between the feature vectors and the user vector. The user vector, as you can see here in pink, is actually a concatenation of blocks of size k. Each block is dedicated to either a combination of 2 features, these are the 3 first blocks, or to a single feature, these are the 3 last blocks. Here, for example, the block size is 3. When a block is dedicated to a single feature, we simply copy the values from the value vector to the user vector. When it is dedicated to a combination of 2 features, we multiply the appropriate entries of the 2 vectors. Later on, this user vector would be multiplied by the relevant ad vectors to calculate the PCTR, as we mentioned earlier. Okay, so I said that this was what we did originally. What was the problem with that? The problem was that this uniform mapping is very restrictive. In a way, by giving each feature an equal space in the user vector, we actually say that all of the features are equally important. We do not distinguish between them. While we know that different user features hold different informative values and they also have different amount of values. Therefore, using a uniform block size k to represent each of the features and their interaction in the user vector prevents the model from reaching its full potential. So we asked ourselves, can we turn this into this? In other words, can we find a better representation, non-uniform presentation of our users by mapping its features differently? For example, what if gender cross age would get 4 entries and gender cross hour would get only 1 entry? Can it improve the results? Does it describe the user better? What was our motivation? First of all, a non-uniform mapping would allow us to add new user features without increasing the length of the model or decreasing the block size k. And therefore, we would be able to add more features and would increase the model capacity. Second, an optimal representation of the user would help us avoid overfitting that might happen when we use the uniform structure and would give us more accurate results. And third, the model size affects many of the system performance measures, such as the training time, the memory consumption, the serving delay, the number of queries or auctions per second it can handle, etc. So, by reducing the model size, we would achieve better performance. So now that we understand the motivation, let's talk about the algorithm. So I'm going to describe DLFM, Dynamic Line Factorization Machine's algorithm. Starting with the uniform structure, the DLFM algorithm optimizes the user vector structure by testing and applying small changes to it every tuning cycle. This procedure is dynamic. It is being done all the time. In practice, the algorithm can remove and/or add up to n vector entries per tuning cycle. Each such change is automatically tested and evaluated before being applied to the model. So let's go over the algorithm. First, on each training cycle, the algorithm identifies redundant entries that can be removed and trains new entries that can be added. To evaluate which entries can be removed or added to the model, the DLFM uses two main components. The first component analyzes the user and the add vector during training and evaluates which entries can potentially be removed, meaning which blocks can potentially be shortened. The second component trains potential extensions for each of the blocks and evaluate the benefit of adding the extensions to the model, meaning expanding a block. Given the results of these two components, the algorithm creates new potential models with different user vector structure that would be trained on the next cycle. In order to do so, we take advantage of the MapReduce architecture of our system, which allows training hundreds of models in parallel. Originally, the system was designed to train multiple versions of the learning model in parallel, each one with a different set of hyperparameters. But now, we support DLFM by adding to each hyperparameter tuning cycle several new models, each one of them with a slightly different user vector structure, and train them alongside the different hyperparameter sets models. I'll now go over the different components of the algorithm, starting with the entry removal component. We will use the following guideline. We would minimize the loss, just as we do during training. Let's go over the loss function. So Y is the click indicator that can be either 1 or 0. If a user clicks an add, then Y equals 1, and we are remaining only with the left element of the formula. Looking at this minus log function, we see that the closer the PCTR we predicted is to 1, which means our prediction was correct, the lower the loss is. On the other hand, if the user skips the add, then Y equals 0, and we are left with the right element of the formula. And looking at this function, we can see that the closer the CTR we predict is to 0, to the right answer, the user skipped the add, the lower the loss is. So we're using this loss function to update the model parameters for each training event using stochastic gradient descent. This is what we do during training. We're also using it to measure the offline performance of our model. Now let's use it for the user vector optimization as well. Let's remember the PCTR formula we saw earlier. I told you we would come back to it. So the inner product of the user and the add vector is actually the sum of entries multiplication. Therefore, we can define the following. PCTR minus I, which is actually the PCTR of the model without the ith entry of the user and of the add vector. Of course, these entries are changing for every user and every add. So for every event, we would have different UI and VI. How do we achieve the PCTR minus I of an event? We would simply remove the multiplication of the entries ui and vi from the inner product we see on the exponent. Given PCTR minus I, we can now define loss minus I of a tuning cycle by updating the loss function to use PCTR minus I instead of the regular PCTR. This value, this loss minus I, represents the loss of a hypothetical model that doesn't contain the ith entry of the vectors, and in which the block of the features that correspond to the ith entry in the user vector is shortened. At the end of each tuning cycles, the entries for which loss minus I is the lowest, since we want to minimize the loss, are considered for removal. So here is an example of how we remove an entry in practice. Let's assume that the loss without this entry, the 0.45, is the lowest. So we first need to find which entries in the feature vectors correspond to this entry. So we can see that the entries that correspond to this entry are these entries in the age feature and in the hour feature. What do we do next? We remove the corresponding entries from the age feature and the hour feature, and the size of the user vector as well as the size of the feature vector would decrease. We would also remove this entry from each of the add vectors, which I didn't show in the slide for simplicity. In the next training cycle, we would use this new mapping instead of the uniform one, and we would look for redundant entries in the new mapping and so on. So you can see here that the block that represents age and hour was reduced to 2 entries. And this is the new user vector structure. What about adding new entries? Evaluating which feature should be expanded was a little bit tricky, since it is not clear how to evaluate in advance the outcomes of a possible change. Moreover, even if it is clear which feature to expand, what should be the initial values of the new entries? If the algorithm initialized the entries with random values, it would result in wrong predictions. If it used small random values, it would take a lot of time for them to converge and to become beneficial. So what do we do with these new entries? To solve these two problems, we designed the greenhouse. What do we do in the greenhouse? A greenhouse is an independent unit that trains alongside the model and grows sets of potential extra entries, one set for each block, which means one set for each feature and each pair of features. Each such entry set includes one entry per each feature value and each add feature. So let's look at the example here. For the gender feature, for example, we grow 3 entries in the entry set. This is the entry set of the gender feature. Why do we have 3 entries? For the 3 values this feature can have: female, male, and unknown. For the hour feature, we grow 24 entries in the entry set, since it has 24 value vectors. For the recombination, for the gender cross hour entry set, we grow 3 entries for the gender and 24 entries for the hour. I hope it is more clear now. So how do we choose which entries to add to the model from the greenhouse? Similar to what we did to identify redundant entries, we now define for each entry set I the PCTR plus I, which is the PCTR of a model containing this new entry set. So the PCTR plus I, we define it by simply adding the multiplication of the UI and VI from the greenhouse to the inner product. As before, we will use the PCTR plus I to define loss plus I. This loss value would be used to train each of the training sets from the greenhouse as if it's part of the model, independently from the other training sets. It would also be used to measure the potential contribution of the entry set to the model performance. At the end of the tuning cycle, the entry set with the minimal loss is considered to be added to the model. So let's go back to our toy example and see how we're adding an entry in practice. So after the training cycle is complete, we have the loss plus I of each of the entry set, which is the average loss of a model containing this set over all the training events of this cycle. assuming that the third entry set was the best. It means that we should expand the hour feature. We would take the potential set of entries we grew in the greenhouse for the hour feature, these 3 entries. And we would push these entries to the model vectors. This, of course, would result in increasing the user vector as well. And although I didn't show it in the example here, we also do the same thing to the ed side, but it's much more simple since we don't have this structure. Once we know which entries can be removed and which set of entries can be added, we can start generating DLFM models. How do we create possible models and test new user vector structures? So at each tuning cycle, 3 potential DLFM model types are considered. Removal model, a model with at least 1 less entry, additional model, a model with at least 1 additional entry, and replacement model, a model that extends the size of 1 or more features at the expense of others. For the removal model, we use the results from the entry removal component. For the addition model, we use the results from the entry generation component. And for the replacement model, we use, of course, the results of both of the components. We remove redundant entries that we get from the removal component and add instead of them new entries from the entry generation component. These models would be trained alongside the hyperparameter sets we mentioned earlier, which has a static user vector structure. This is how it works. At each tuning cycle, hundreds of models are being trained in parallel. At the end of each training cycle, all of the models are evaluated and the best resulting model is selected. Then, the system virtually duplicates the best performing model and resuming its training with multiple new hyperparameter sets. These are the static models you can see on the left. We support DLFM by adding to each tuning cycle the 3 types of model we mentioned, the removal, the addition, and the replacement models. These models differ from the best model as well as from the static models in their structure. At the end of the next tuning cycle, all of the models would be evaluated, and then the best model would be chosen. If the best model is one of the DLFM models, then the training during the next cycle will continue from this model structure, since we would duplicate it. Okay, so before we continue to the results, I would like to mention that our removal and generation techniques can be applied to other factorization machines as well, simply by defining the loss minus I and loss plus I based on their loss function. So now let's see some results. I'll start with the online performance. So to evaluate the online performance that determines whether the DLFM algorithm is pushed into the production system or not, we launch an online bucket serving a portion of Yahoo Gemini native traffic and measure the revenue lift in terms of average cost per 1,000 impressions, CPM, with respect to the production model. In this graph, we can see the daily CPM and CTR lifts of the DLFM bucket when compared to the baseline. On average, the online DLFM bucket showed 1.46% CPM lift and 2.15% CTR lift. Such a CPM lift translates to many millions of dollars in yearly revenue. I would also like to show the changes to the user vector structure in our production model several months after deploying DLFM, starting with a uniform vector allocation, where each block is of size k, and the total size of the vector was several hundred entries. The algorithm has continuously removed, added, and replaced the user vector entries while optimizing the performance with each tuning cycle. In the following table, we can see a snapshot of the user vector structure. Each table entry, aij, represents the ratio between the original size of block ij, which belongs to feature I and feature j, which was originally k. It shows the ratio between k to its current length. where values smaller than 1 indicates that the block was shortened, and values greater than 1 indicates the opposite. So here in the table, the darker the entry is, the higher the ratio is. So on the diagonal, we see the entries that belong to single features, and all of the other entries are interactions between two features. You can clearly see that the user vector has gone through many changes, reaching its current structure. More than that, if you would look at the entries that belong to the page section, okay, it would be the column of the page section and the row of the page section, you would see that the page section holds the largest share of user vector entries, which indicates its complexity. This feature has more than, it has few thousand values, and also it indicates its significance. This didn't surprise us, since other feature selection methods have already indicated the importance of this feature. Now we can see it in the structure as well. It is also interesting to see that several of the blocks were reduced to 0, meaning that the interaction between the features did not contribute to the model prediction nor improve its prediction accuracy. Okay, so that's it. Thank you very much for listening.